Thanks very much. Well, I'm not sure if you noticed, but there was a striking similarity between that being that showed up on the wall and myself. But in any case, the reason I'm here today is to try to convey to you the modern understanding of gravity that we as physicists have right now. But before I begin, I should mention that even though we know a lot about gravity in many different aspects, even though we have observed it in many different ways, it continues to be the most mysterious force in the universe. But before I speculate about what that could actually be, I will start by explaining and telling you what we actually know about gravity. And the most common observation that we know about gravity is that bodies fall. So right now, we're always being driven towards this big rock that we call planet Earth. And if, for instance, I lift my feet like this, there's a certain amount of time that I'll be able to keep going like this without being, again, driven towards the Earth. And it's not just in this way that we're always driven towards the Earth and having the experience of falling. Even though we might not sense it, we are on planet Earth, and planet Earth itself is falling towards the sun. It doesn't go directly into it because it also has a velocity, so it whirls around, but it's falling towards it constantly. And the sun itself is falling towards the black hole in the center of our galaxy. So this is a bit weird, but in fact, the future of humanity in the long term is either to fall into a black hole, either to freeze to death because the expansion of the universe will lead to a very cold and dark place, or to melt into some kind of soup because the universe will just shrink and heat up again. It's sad news, but at least today you have the opportunity to drink a cocktail and forget all about it. Anyway, the most important question that I'm going to address today is why do we fall? And the answer to that question has changed over time. And as I said in the beginning, it will change in the future, sooner or later. But who answered this question for the first time in a way that we find extremely reasonable was Sir Isaac Newton in the 1600s and 1700s. And he is here portrayed with many different objects around him: a telescope, the Earth, the sun, the moon, an apple, a bunch of books, a prism with light, diffraction, and even the ocean. And this is because he made contributions to our understanding of all these things from a physical point of view. And in a sense, he married abstract thinking, mathematics, with the physical laws in our universe, and both on Earth and above in the heavens. But one of the things he is notoriously known for is of thinking so deeply about all these things underneath an apple tree. And at some point, an apple fell on the ground, and he said, well, wait a minute. I mean, why is this apple not floating in space? And he conjectured that there was a force that somehow pulls the apple down towards the Earth. And he wrote this very famous equation that we as physicists have either imprinted in our brains or tattooed in our bodies. I have one, but I'm not going to show it to you. Maybe later, if you give me enough drinks. And this equation says something. It says that the force, this F, is proportional to the mass of two different bodies. So if you have a body with mass 1 and a body with mass 2, the force that they feel is proportional to the product of those two masses, and it weakens with distance, and it's stronger the closer you are to the other body. And there is an important aspect of this equation, which is G, which is called Newton's constant, and it's what we call today a constant of nature. We think, all our observations indicate that this constant is there no matter where in the universe. There's maybe just a couple of German people who disagree about that, but forget about it. In all the observations we have, is that this is constant. So what does this mean in practice? That if you have a body, m1, on one side, a body m2 on the other side, they will feel a force proportional to those masses. Now, you might wonder, well, if that is the case, and you're very close to each other, as I can see, why are you not attracted to each other? I mean, I know that this is a weird way of saying attraction, because I believe that you're here to hear about gravity, not for something else. But you can think, why are you not attracted? And the reason is that that g constant there is really small. Really, really small. It's 0.00011 times and then a 6. So you need a huge mass to be able to experience it, like the mass of the Earth. And so, gravity, as we know it, is the weakest force in the universe. And the proof of that is, I can show you right now, is this. This is 0.2 kilograms, this small remote. I'm going to put it on the floor here, being pulled all the way by this huge mass, which is planet Earth. And now, with my huge, muscly body, I'm going to take it and I managed to pull this out of the Earth. So you can see, it's really weak. Thank you. Thank you. Yes, very proud of it. So to experience, you can start having the feeling that to experience the acts of gravity, you need humongous mass, humongous bodies, like planets. So if you want to experience the difference between how you feel depending on the force that you're being acted upon, you have to go to different planets. So let's make here an experiment. Here you see many, many planets. This one here, okay, wait a second. This one here is Pluto, you can see, and further along you have Jupiter and Saturn, which are much bigger planets than Pluto. Pluto is a very small planet, has a very small mass. And what we're going to do is that we're going to drop a ball 1 kilometer away from that planet, let it drop, and see how fast it goes down. Because how fast it goes down depends on that force that you will experience differently in different planets. So look at Pluto over there, and for instance at the Sun, which is much bigger, and see how fast the balls drop. So it already reached the Sun, and it's still going on in Pluto. It's very quick in Saturn and Jupiter, and now Pluto is still going on. Several seconds and seconds. In fact, about 1.5 seconds for the ball to reach the surface of Pluto. So you have time to smoke a cigarette or drink a cup of coffee before you fall on Pluto. So this is one, you can see that to experience this type of force, you really need big objects. And there is more things that are strange about gravity that we know are true. For instance, gravity does not care whether you're a human being, an apple, or a feather. You will always fall at the same rate if you are able to remove the air in the room where you're falling. So this is an experiment in where people removed all the air, so it's a vacuum chamber, and they're going to drop an apple and a feather at the same time and see what happens.
4. Cameras on. 2, 1, release.
The objects fall at exactly the same rate. This is how gravity works. Now, what was special about Newton is that he kind of unified heaven and earth, in the sense that the concept of laws of nature came from him. And what does that mean? It just means that the laws that govern the movement of physical objects on Earth are the same laws that govern the movement of planets in space. This was an enormous achievement at that time. Now, is this everything that gravity is about? And no, it is not. So to see that, we can have to go to Newton's point of view on all of this. And his point of view was that space itself is not changeable, is metaphysical, is absolute. It's like a stage that doesn't change in time or even in space. And time itself is exactly the same thing. It's like a clock that has been ticking since the infinite past to the infinite future. It does not change. And so bodies that are moving in that space, moving, doing whatever they're doing, they do not affect neither space nor time. Now, already Newton knew that this could not be completely correct. Because if you think about it, how does the Earth know that it's being attracted towards the sun? How does it know that it's feeling some gravity from the sun and knows exactly when to turn when the sun says, hey, you have to turn right now? It does not make sense. And it took 200 years until Albert Einstein came in, who thought deeply about this question, and he realized that there was something fundamentally wrong about it. So he wrote a new equation, which is now called Einstein's equation. It looks a little bit more complicated, but it's very easy to read. On the left-hand side, there is some object that says how the shape of space and time is. And on the right-hand side, there is an object that says what type of matter or energy or stuff it's inhabiting that space and time. So what the equation says, in essence, is that the geometry of space and time is determined by the stuff that lives in it. So this is easy to see in pictures. For instance, if you have the Earth in space, then it will curve space in that specific way. The weight of it curves space and time around it. This is the same thing, but now an illustration in 3 dimensions. So the whole space and time is warped, it is curved. So now you start understanding why the trampoline is a useful medium to explain gravity. Because as soon as you go into it, you make a dent in space. So in the same way, if you put a bunch of dancers in it, space is going to go down. And it demonstrates one of the nice or interesting features about this completely different point of view on what gravity is. It's no longer a force. It is something that curves space and curves time that creates the attraction between two objects. So now we can go back and say, and ask the question, are we actually falling, or are we following our own path in space and time? And we are following our own path in space and time. So here you can see the Earth creates some kind of curvature, and if you put an object or a person close to it, that person will just follow space and time as it goes along. And that's why it feels the attraction towards the Earth. Now, this is very clearly seen here in this small video where a high school teacher in the US got a rubber sheet and now put some objects in it. You can see what happens.
And so you put matter and it warps space-time. And so if I have another object, it also warps space-time. They feel that and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly.
So this is the same thing that would happen in a trampoline. You put a bunch of people in one part of the trampoline, a bunch of people on the other part, they sort of warp space and time, and then they feel this force, and they get together. So this is the whole principle about what Einstein had to say about this. But many things happen that come from this. For instance, what happens if you put a lot of people or a lot of mass concentrated in the same place? So you put a lot of dancers, 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 and then all of a sudden you get a black hole. what does this, so there's a joke about this, because when I first mentioned this, they told me there's not enough budget to create a lot of dancers on the trampoline. But in any case, if you put a lot of matter concentrated in the same place, you create a black hole. And what does that mean? It means that there is this huge dent, this throat that goes on and on indefinitely. And if you go near it, you basically fall and you're not able to escape. And the striking thing about this is that it's not just matter, it's light. So light, if light approaches, it just keeps falling. It's not falling, it's following its own path. It just keeps going, disappears. And that's why we perceive it as black. So we have detected it recently, taken a picture of it, and this is what it is. There is this black circle in the middle, and then this thing you see around is what is the plasma that is orbiting around it. But in the middle, there's nothing. It's just gone. It's absolute darkness. In practice, this black hole is actually kind of rotating, and the plasma rotates around it, like in this simulation. But a lot of different or strange effects are felt around or are perceived around this geometry because it warps space-time so much. So for instance, in this animation, you can see the Earth going around a black hole. And as it goes around, the light is bent around the black hole in such a way that it creates this funny effect that you can see. The same thing, if you could look at this sort of accretion disk around the black hole, you will see part of the back of the accretion disk going above and part of the back going below. And that's why you see the disk all over the place in this picture. The same thing would happen, for instance, if you would fall into a black hole. The space around it, as you fall, gets really, really distorted until you reach the event horizon. And then we have absolutely no clue what happens. Now, another interesting thing that Einstein tells us is what happens if we move in that space. And what happens, it's very similar to what happens if you throw a rock on the water. It just creates ripples in space and in time. If you have the Earth and for some reason there was a ripple in space and time traveling through and going through the Earth, the size of the Earth would get distorted as the wave passes through. And this is something that you can, in fact, feel very much in the trampoline, because if you make a jump on it, the trampoline is moving, propagating your wave through the space. Now, there are many types of events that create these waves, and the most striking one is when two black holes collide. So in this video, you'll see two black holes that are orbiting around each other, until they merge. And as they do that, they warp the space and time around them in this way that we actually have recently observed. You can see it in a different way if you also would look into the sky itself and project all the stars around it. Then the whole visual field that you would get would also get extremely distorted. And the interesting thing also about this whole principle is that as we move, us as people move in space and shake our hands in a specific way, we're all creating gravitational waves that are traveling through the room. But we don't feel them exactly because our masses are so small that the effect is negligible. So you need enormous objects to create such a thing. We can also transcribe this movement into sound, and this is one of the most charismatic sounds that came out of some scientific endeavor. This is the sound of black holes colliding. So as a challenge that I leave to you is that when you listen and hear and see the dance performance, you try to identify this sound in the music. What about the universe itself? Einstein's equations is not something that applies just to a black hole or to the Earth or to the Sun. Einstein had also had this idea when he first discovered his theory. Well, he thought, what happens if I put the entire matter of the universe and energy in it? Can I determine the shape of the universe? And indeed, nowadays we know that yes, we can. And the picture we have is a picture in which if we go back 13.7 billion years, then the universe started shrinking and shrinking and shrinking until what we call the Big Bang singularity, in which space and time were born. Now, we don't know if this singularity was actually there, and in fact, what we think is that it is not there. And when we go back into the past, 13.77 billion years ago, something else has to replace Einstein's gravity. Another theory has to replace what happened in the first microseconds after the universe was born. We do not know that for sure. But we do know, and we can see today, that our universe is continuously expanding. The amount of space is expanding as we go because of something called dark energy, and galaxies are moving further and further apart from each other. And all we know right now is that this can continue forever. We also know that it is possible to understand a little bit, in fact, quite a bit, of what happened during those first seconds where the universe was born. And this is a map of what we call the cosmic microwave background, which is basically the temperature of the radiation that was released during the process of the birth of space, of the birth of the universe, and this radiation has cooled down over time with the expansion of the universe, and now reaches us as a temperature which is just 3 Kelvin, almost close to absolute zero. But we can see it, and we can understand it in many ways of how this structure has given rise to the large-scale structure of the universe, the galaxies, the planets, etc. So a lot of it we can understand. And I like to think of it like right now, right here, we are receiving this cosmic microwave radiation. So the entire history of the universe is actually in this room. Now, the reason why we don't just look at this room is because there's a lot of noise. As you probably know, there's radio signals from DR P1, P2, P3, P4. Carlos also has his cell phone on, and he's calling all the time, so his network is interfering right now in this room. So we don't put our telescopes here, we put them on top of Chile in the mountains, or we send them into space to have clear signals about how to detect this. Now, I want, in the final time that I have here, speculate a bit about what we do not yet know about gravity, and perhaps of a new understanding of what it actually is. Now, this is a picture of a black hole, again, but now this sort of radiation you see around it is not what I mentioned before as the plasma, the stellar debris that is going around this black hole. This was something that Stephen Hawking conjectured, and is the fact that black holes are probably not exactly black. They radiate energy, like anything that is hot and has a temperature radiates some electromagnetic energy. We don't know if it's true, but we think very much that it is. And this is important because all of a sudden black holes are thermodynamic objects, just like a cocktail, a piece of ice, or something else. And if they're thermodynamic objects, they also have something called an entropy that counts the type of configurations it can be in. It doesn't matter so much what it is, but it is a thermodynamic object. And what we know about it is that this entropy is somehow just encoded on the horizon. Typically, the entropy of any object is encoded inside it, in the volume, but this is just on the area. And so people started thinking about whether there is a different way of viewing things, that perhaps to know what's inside the universe, I just need to look at the edges, at the boundaries, at the surface. And in fact, people came with this concept of holography. So you probably have seen holograms. In a long time ago, we used to have holograms in our credit cards. And the idea of a hologram is that it's a two-dimensional surface, but if you shine light on it, it projects a three-dimensional image. So somehow the surface knows about the three-dimensional image, even though it's just two-dimensional. So you can think whether gravity is like this, whether just a two-dimensional surface is able to project gravity in three-dimensional space. Now, it looks a bit far-fetched, but we have mathematical models that express exactly how this can be. And funny enough, it's a completely different language, because on this surface, there is no gravity. There's other forces, other particles, and if you collide particles in that surface, it's the same as creating a black hole in three-dimensional space. So it's almost as if we went back to Newton and we thought, and we said, well, actually he was not exactly incorrect. There is both space and time absolute on this two-dimensional surface, but then there's a lot of other particles and forces that somehow mimic the effect of gravity. Now, we don't know if this actually applies to our world, because these models that we have are not describing our universe. But people are trying to understand whether on the edge of the universe there is a theory that can actually describe the gravity that we have nowadays in our universe. And this would be a completely different way of looking at it again. And this is very much inspired by what we call nowadays string theory. So string theory is a theory in which all particles, all forces in the universe are created by the oscillations and vibrations of small loops that we call strings. So the space and time and gravity are sort of the collective behavior of these strings. They oscillate, and they create space and time at these enormous scales. But if we would be able to go to what we call the Planck scale, very, 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 very small scales, with a microscope powerful enough to do that, we would then be seeing small little loops of string wiggling, and creating gravity. We don't know if this is true, but it could be. One of the interesting things about this, and weird things, is that if it is true, then we live in extra dimensions, many more dimensions than just 3 spatial dimensions and 1 time dimension. In fact, 10 dimensions in total. And if that's the case, and this is what I spend a lot of my time doing, then there might be different kinds of universes out there in which the constants of nature are changing from universe to universe, including the constant of gravity, and we just happen to live in one of them. We don't know. What I also spend a lot of time doing, in a very schizophrenic mode, after I have breakfast, is trying to find different black holes out there. If this theory is right and we live in 10 dimensions, then black holes are not necessarily spherical. They're not necessarily like a circle. They can be a torus, like a donut. They can be a disk. They can be what we call helicoids. And they can be what we call catenoids. There's many possible geometries for what black holes can be. And maybe one day we'll find that these things perhaps actually exist. At least I can say I'm paid to do this, so it's not a bad thing. So before I finish, this is my last slide, I wanted to say that we understand gravity very well, but this is not the end of the story. Sooner or later, we'll have another conceptual revolution caused by all these ideas I presented now, or maybe others, but that are needed to understand what happens exactly near a black hole and what happens exactly at the beginning of the universe. So, thank you very much.